what you have learned from previous 2 days. We talked about what algebraic effects are. That comes with a set of operations with signatures, and there are some axioms which you expect them to respect. And we talked about effect handlers in the last lecture and how they give interpretations to operations. And we have seen lots of examples where we can use algebraic operations to write effectable computations that get handled later by handlers. And we have seen that handlers can be very easily nested and composed, and you can use them to handle programs that can have multiple operations. And my plan for today is I want to give you a very quick overview about effect type systems, especially that people use to give algebraic effects types, and how we can prove syntactical type safety. And afterwards, we'll be talking about how effect handlers are actually implemented in practice. And if time allows, we can try to build our own library for effect handlers in Haskell. So to start, we talked about the syntax of expressions already. So that's from last time. So we have in the expressions constants, variables, lambdas, applications, if-then-else expressions, operations, handlers. And only constants and lambdas are considered values. And there is syntax for handlers, which comes with an operation clause and a return clause. So here, for simplicity, we assume that each effect only has a single operation. But in practice, you can imagine that an effect actually comes with multiple operations, right? Because in the case of state, we would assume you have get and set. And that's why when people talk about effect type systems, there is usually this effect label. So I'll use this L. For example, you can consider state is the actual effect in your type system. And if you have state available, as the effect of the program, then you can use both get and put, and they should be accessing the same stateful resources. And once we have effect labels, as we have seen, well, your program can perform multiple effects, right? Maybe you have state, maybe you have reader, maybe you have exception. So we need a way to express a collection of effect labels. So here I use basically the syntax what people use for row effects. So here, in this case, this can either be empty or it is the extension of a label with another effect collection. So I use epsilon for effect collection and L for label. Now you got a sequence of effect labels. And of course, now you have the question, what exactly is a collection of effects? How should we express that? And there are multiple different ways that they all come with their own advantages and disadvantages, and they are actually implemented in different languages in different ways. For example, you can represent effects as sets, which is implemented in the language F. And if you represent them as sets, then that means there is no duplication in your collection of effects, and you have constraints like sub-effecting, like subset in your program, and you have to have a way to express that as a constraint, for example, in your type system. And more commonly, people also use row types for effects. So you can consider them as basically like extensible sets. Like you can have some labels already in the set, but they end with a polymorphic tail that says you can have no effect. And that's a way to use row polymorphism to express row polymorphism to express effect polymorphism. And even if you do it that way, there is still this question: do you allow duplicate label in your collection of effects? And different languages make different decisions. So if there are no duplicated labels in your row types or effect, then this is considered as simple rows. And this is implemented in languages like Linux. And if duplicated labels are allowed, then it's called scoped rows, and that's what's implemented in Coca. So the system we will see later actually implements scoped rows, just as an example. But different representation of effects will come with different type systems. And now, with the definition of effect, we can look at the definition of types. So here I give just some simple examples. We assume constants types like int and a bool, and we also have a function type. And this function type will look slightly differently from the function types you will see in other systems. So here, this function type says, this is a function that takes an argument of type A. And when you provide this argument, this function will run. And it may perform effects, as in this effect collection epsilon. And then the return result of this computation has type B. So in other words, now a function must explicitly specify that what kind of effects can be performed in the body of the function. So you can actually look at the type signature and then you can see what effects are allowed in this function, and if this epsilon is just the empty set, then you know this function is pure. So here are the typing rules in this effect type system. So these are mostly standard ones that we haven't, the rules for op and handler in the next slide. So let's first read this judgment. So maybe you have seen simply type the number of characters, so you will know that, okay, this judgment says under the typing context, the gamma, so gamma basically just maps term variables to their types. This expression E has type A. But what's new here is this judgment, I put here a bar, and then afterwards I have an epsilon. So this judgment is saying E is an expression of type A. In the meantime, evaluating E might perform effects in epsilon. So you have to keep track of the effects that will be raised in the effect type system. And let's go through these rules. So the first two rules are not that interesting. I'm going to just as an example. So of course we all know true has type bool, false has type bool. But what's special here is I put an epsilon prime as the effect of these values. Of course, if you are in a set-based effect type system, you will put an empty set because they are values, they don't perform any effect. But as we will see in this type system, there are rules where you would have to have the same effect over the places. So here I will just say these values, they can have any effect. You can consider that they may perform any effect, while in reality, they are not performing any effect. So you can consider this epsilon as an over-approximation of what effects can be performed by this program. And similarly, in the case of variables, we just get the type of x from the context, and it doesn't perform any effect, but we will just say it can perform any effect in this epsilon prime. And now we move to lambdas. So in the case of lambda, we would like to put this x of type A into the context, and then we type the lambda body B, and then say B has, let's say E has some effect epsilon. And after that you know, okay, the body of this function will actually perform effect epsilon. Once you get back, you have to keep track of the effect of the body. So this is where you would form this function type that says lambda, this lambda is something that takes an argument of type A, returns the result of type B, but it may perform effect in epsilon. I think here I'm missing another bar in the end. There should be another bar and epsilon prime, because lambda is also a value. So lambda itself, you can also consider that it can perform any effect. And that epsilon prime doesn't have to be the same as epsilon, because this is a value. It actually doesn't perform effect, but you can over-approximate the effect set to anything. But this function type has to remember that when this function is called, it will have this effect, epsilon. And now we move to this application case. So in this application case, there are many epsilons going on, because you first need to type check E1, and when you type check E1, you will get an epsilon from that function. This function says, if you get me an argument of type A, right, my body might perform effect in epsilon. And also, this E1 itself may not be a value, right, because you may have to do some computation in order to get this function. So this whole E1 also has type epsilon. And the argument E2 will have the required argument effect A, and then it also has effect epsilon. And now the overall effect of this whole application is epsilon. Yes?
So for the application rule, all the epsilons have to match?
Yes. All the epsilons have to match. So this is the way effects are represented in the rho-based type system. And one advantage of that is now your type system only needs to do unification for type inference. There is no, you don't need to reason about subsets or different forms of subtyping other than polymorphism. But this is also why, for example, we allow an arbitrary epsilon for values, because there are cases that you have to actually pretend that those values actually have effects in order for this application rule to apply. Yes?
If you have an epsilon that is, so in the lambda rule, if you, I remember you said there's like, I'm missing like bar epsilon prime. If that epsilon prime is different from the other epsilons, would you ever call that lambda, or would you not be able to use it?
So when you actually use that lambda in that application rule, that epsilon prime has to match that epsilon. Yes. So this is also a known issue. Sometimes people call effect pollution, because now you would require that those pure values to have some effect as well, and while they don't. And this the whole purpose of pretending that they have values is just to make the system, the program type check. But again, this is a rho-based type system. In an expected type system, since we're working a different way, in the value case, you will just say this is an empty set, and then in the application, you will have 3 sets you connect from different places, and then do a union in the result. But now you have to reason about set relations in your type system. And the if then else expression is the same as applications. So in this set of rules, you can see that we are basically just propagating epsilon. That nobody can ever actually do anything based on this epsilon. Yes?
In the previous slide, so when we are making arrow type, the epsilon beside, like the epsilon after the vertical line is not there, but we need that in the application. So, like, how
Yes.
do we make the first premise of the application if we can't?
It's a question about this lambda rule that is missing a bar and epsilon
Yes,
prime. Yes, we should have a bar and epsilon prime here. That's a typo. And if we actually want to do anything interesting using these epsilons or based on these epsilons, we need 2 typing rules for the operation and for the handler respectively. So in the case of operation, whenever you do an operation by providing the argument E, the first thing we do is we need to get the signature of the effect. And here I'm just assuming there is a global context sigma that stores all these signatures for operations. For example, state would be, put would be something that takes the state, give you back a unit, get would be something that takes the unit and give you back the state. And the most important thing here is, if O is an operation that belongs to this label L, so consider that this L is state and this operation is put, then this L has to appear in that epsilon. So you have to keep track in a type system that there is an operation that has been performed and the operation belongs to this label L. So later, whenever you want to run this program, for example, you have to provide a handler that will actually handle this effect L. And the handler rule is a bit more interesting. So here, if we just look at the first premise first, so this rule says we can handle this commutation E using the handler H. And we first type check the expression E, and we get back some type C. And also, we know that the expression E will perform some effect, and we know that this L has to appear in this effect set. And if that's the case, then what happens? Well, this handler will, if we just look at the effect first, the output, the effect of this expression has both L and epsilon. But in the output, the handler will eliminate that L, because handler says, now L has been handled by me. And also, because we have return clause, the return clause can change the return type of an expression, right? Like we have seen with exceptions, you can change it to a maybe, or you can change it to a list. And the second promise is basically how we type check handlers. And how we type check handlers, so this judgment can be read that we type check the handler H, and H is something that handles a computation of type C. And it will return you back a type D. And we keep track of the effects that are actually performed by this computation. And now you can see that in the return clause, for example, we will know that the computation have type C. So this X is going to be bound to type C. But the return clause can change its type to D. And because L has been handled, all you can perform now is just epsilon. And again, we get the operation signature from the global context. And now we can check this operation clause. From this operation clause, this X as an argument to the operation is bound to the type of the operation argument, in this case, this AI. And then there is a type for discontinuation. And this continuation is something that is waiting for the result of this operation. So we can type it as a function that waits for something with type BI. And afterwards, it should also return a type D because we reinstall the handler. We are in this deep handler semantics. As long as we reinstall this handler, the return type, the overall return type of the computation is going to be D. And then this whole thing should have type D. And you can see that this continuation can perform more effect, but just in this epsilon, because again, this label L has been handled. So this set of rules are the complete set of rules, more or less, that you can write for a role-based effect type system. So I'm not going to give you other variants for other representations of effects, but you can write slightly different typing rules for set-based effects or simple role-based effects. And again, they all come with their own advantages and disadvantages. So I will just very quickly speak about type safety, specifically syntactical type safety, and how we have to change the statement in order to prove type safety. So first, type preservation. So type preservation says if you have a program with that type A, with that effect epsilon, and I evaluate it, I reduce it to through one step to E prime, then E prime has the same type A and has the same effect epsilon. Right? Like nothing is special here. And let's say now we want to prove progress. And this theorem says, well, if E is the well-typed expression of type A and effect epsilon, then either E is a value or there exists E prime such that E reduces to E prime. Is this statement correct? Someone nodding? Yes?
So if you send out an operation like an effect that's not handled, then you just stop.
Exactly. What if there is an operation in epsilon that is not handled? Because the program says I can perform effect in epsilon, and there is no corresponding handler. Because if there is a corresponding handler, then I should not be seeing this epsilon in the overall type of this program. So we will have to slightly change this statement, and this is how you would actually prove progress. And I call this progress with effects. And it basically adds a third possibility to this statement. So if E is an expression with type A and effect epsilon, then E is either a value or there exists an E prime such that E reduces to E prime, or E has this particular shape. And this particular shape says, now basically I'm stuck with an operation that is unhandled. So specifically here we have this shape of E that says you are currently evaluating operation op with some value V under this whole evaluation context, this capital E. And I know that because this expression E can only perform effect in epsilon, I know that op must be one of the operations that belongs to one of the labels from this epsilon. And I know that there is no handler in the evaluation context that can handle this op. Because otherwise, if you can handle this operation, you can just reduce, right? You would use the second case instead. And this third case only talks about the situation where the program is actually stuck because of defects. And from this statement, we can derive the real progress we want. So the real progress we want says that, well, if E is an expression with type A, and I know that it does not perform any effect, or all the effects that it has performed has been handled. So the overall type is just an empty effect set. If that's the case, then I know that E is either a value or it reduces. And you can directly apply this progress with effects to prove this. Because in the case this epsilon is empty, the third case is simply not possible. Okay, so that's a very quick overview of the effective text system and a very quick overview of the syntactic text safety. But of course, if you actually want to prove it, you will have to do induction and then see how the steps go in the proofs. But I think that will be what will be covered in this lecture. So hopefully this gives you some rough idea about how effective text systems work. And I do have this slide here. It's just deep down in my slide deck, but I got asked this question on the first day and on the second day, which is how to compare algebraic effects with monads. So the quick answer is algebraic effects are more modular and composable because you can very easily compose them. You can write the effective for computation without worrying at all about how those effects are going to be handled, or in which order they are going to be handled. While with monad transformers, for example, you will have to worry about the monad transformer stack, and then you have to do lots of manual lifting if you have multiple monad transformers in your stack. But monads themselves are more expressive, and then they can express more programs that will be difficult to express directly with algebraic effects, especially things that people call higher order effects. Yes?
Is this because when you have algebraic effects, you can't combine them too much, or is it that this is the reason different? Or am I wrong that you can't combine them?
If you have different handlers, you can always combine them. And you can combine them in different orders and get different behaviors. So here is this paper from Haskell 2019 that aims to answer the exact question. So you will see some of the examples there and some of the analysis they did to study the relative expressiveness of algebraic effects and monads. All right. Now let's move on to the last part of the lecture, which is about how to implement effect handlers. So we talked about algebraic effects and effect handlers. We talked about that the operational semantics, how the operations are actually handled by the handler, but how do people actually implement effect handlers in different languages, for example? So one thing that you may have noticed from the operational semantics is that if you actually want to implement effect handlers this way, it's going to be expensive. It's going to be expensive because there are two potentially expensive runtime operations. First, well, when your operation is performed, you want to find the handler that will handle this operation. So you will have to traverse this whole evaluation stack and then try to find the innermost handler that corresponds to this operation. And after you have found it, you have to capture this whole delimited continuation and pass it as an argument to this function f. And capturing the evaluation context is also expensive in practice because you have stacks, you have registers, you have to store the state of everything of the program has at the moment, so that whenever the computation is resumed, you can go back immediately to the point where the program is resumed. So how does well, I mean, we have seen that this expressiveness is actually needed, right? For example, with this all choices example we have seen yesterday, you actually want to capture this continuation, and you actually want to resume multiple times. And when you resume multiple times, you would expect that the program state that is captured by the key K should be exactly the same. So you will have to capture the state and recover it whenever you resume. So how do people actually implement effect handlers? Well, there is a very rich body of literature on this topic. So the very first implementation strategy people tried is continuation passing style. So basically, you can elaborate effect handler programs down using continuation passing style. And the advantage is now you can implement effect handlers in whatever platform as long as they have sort of higher order functions that you can use to implement continuations. But of course, the cost is now you have allocated lots of the continuations and you have to capture the closures, and there is a huge cost for the closure allocation. Although some of the cost can be eliminated if you have partial evaluation. And the continuation passing style is implemented, I think, in the Linux programming language. Right. And there is a paper from 2017 about that. But of course, you could say, well, Linux, maybe is a mature research programming language, but in reality, if you actually want to use effect handlers for anything real, then what should we do? So in OCaml, people implement effect handlers using what they call segmented stacks. And that is a very efficient way to implement one-shot resumption. So what is one-shot resumption? That basically means you can only resume once. You cannot resume multiple times. So the handler, like all choices, will not be supported. But the advantage is one-shot resumption can be implemented very efficiently. So to give you, to demonstrate how things work in OCaml, so let's consider that we have this evaluation stack. So the stack grows from top to the bottom. So at this moment, we are evaluating this operation with argument B. And we have multiple handlers in this evaluation stack. And all these white ones, they are not handlers. So how would OCaml represent this program? It will look like this in OCaml. So basically, the evaluation is organized into a list of what they call fibers. And each fiber starts with a handler. And now, whenever you perform an operation, you can search for handlers very efficiently because you can just look at the head of each fiber. And you can find the corresponding handler. Let's say, in this case, the top handler is the handler that will handle this operation. So you have successfully found it there. And then what happens? Well, you know that this handler has the operation clause for the op you want. And let's say this operation clause is f. And f is going to take the argument of this operation, in this case b, as well as the continuation. Then, on the next step, this program will look like this. So what happened? We basically inserted this f as an additional frame at the bottom of the first fiber. And we apply this f to the argument to this operation, and we are going to bind this continuation k to this whole thing. Right? It's still the same fiber, now just created an additional link. And this continuation is waiting for the result of this operation. And let's assume f looks like this. Like it takes the argument x and the continuation k, and it returns x plus k0. Then what happens? In the next step, you know that this x plus is going to be pushed into this evaluation context. So I will put it as v plus because this x has been substituted by v. But you know now that this continuation is taking this 0. So you can immediately resume directly just by putting 0 at the bottom here, and you push v plus here, and you get back to your stack of fibers. So this is a very efficient way to implement one-shot resumption, and you don't have to capture the program state in order to recover it multiple times. But as long as you resume, this whole stack of fibers is going to link directly back into the evaluation stack. And this is also because basically OCaml will give up on multi-shot resumptions. There is actually a magic primitive that you can use to manually clone the continuation if you really want. But then there are lots of bug reports about that language primitive. And there are other languages too, and they do slightly different things. So in this effect language, people implement effect handlers using what they call capability passing style. I think this is also very similar to what actually gets implemented in Scala now. But it comes with a slightly different semantics of effect handlers. So that's something we will not talk about in a lot of detail. But basically, in this standard semantics of effect handlers, if the operation is performed, you always search the evaluation context to find the innermost handler for this operation. But in this capability passing style, this handler is decided lexically. So it's decided lexically which handler is going to handle this operation. And now, of course, it also comes with complexity that you want to make sure the handler does not escape in the runtime. And because we have some practice about algebraic operations and handlers, based on this practice, we can also do a lot of program rewriting. And that's basically source-to-source program transformations. And you can consider this as orthogonal to the other implementation techniques, because this is mostly a way to do optimizations and to actually try to implement things more efficiently. And lastly, I work in this language called Coca. So it's a strong functionally programming language that comes with built-in type effect system and built-in support for effect handlers. It's developed at Microsoft Research by